I want to start talking about some of the basic properties of the cross product. The cross product is only valid in three-dimensional space. So to start with, let's talk about three-dimensional vectors. When I'm dealing with two-dimensional vectors, I write them in terms of my component vectors, I and j. But whenever I'm dealing with three-dimensional space, I actually have three different directions, all orthogonal to each other. In general, we have the x vector, the y vector, and the z vector. I and j are unit vectors along x and y. So here we have I and j. To correspond with that, I need a unit vector along z, and I'm going to call this k. So in three dimensionals, our vectors are of the form a times I plus b times j plus c times k. To start with, I want to look at taking the cross product of just these vectors, these I, j, k. One of the easiest ways to do that is to put them in a circle with arrows going clockwise. As we move around this circle, we can determine cross products. So I crossed with j would give me k. J cross k would be equal to I, and k cross I would be equal to j, since all of these move in the direction of these arrows, clockwise. If instead I want to think about moving the other way, moving counterclockwise, I could have I cross k. Since I'm moving counterclockwise, that results in negative j. K cross j, since we're moving counterclockwise to get from k to j, that would be negative I. And finally, j cross I, since once again we're moving against the vectors, we're moving counterclockwise, that would be negative k. Using this idea, I can see that the cross product is not commutative. I have I times j is equal to k, but j times I is equal to negative k. In fact, the cross product is anti-commutative. Let's look at a few other properties of the cross product. My first property is the anti-commutative property. U cross v is equal to negative v cross u. Changing the order will change the sign of the cross product. Another one, if I cross any vector with itself, I will get the zero vector. U cross u is always zero, no matter what vector u I start with. My third property has to do with scalars. It says I can move scalars in and out of a cross product. So taking the cross product and multiplying it by a scalar, I could have scaled u and then took the cross product, or I could have scaled v and then taken the cross product. These are all equivalent. My final property is the distributive property, u cross v plus w. And this does in fact obey the distributive property. This is u cross v plus u cross w. So these are my four big properties of the cross product.